right. Good morning, everybody. Sorry I'm a little late. I blame Chick-fil-A.
Oh, not blaming Chick-fil-A.
Yeah, man. I had to go get my
We
kids
had
some
a free
breakfast.
class today.
Oh, no. No free classes. You paying for it. Why would it be free? Uh, Nah, they didn't have the curbside pickup, so I had to get in a line. That's not good. All right. We jumping right in. We've been working on SN1 and SN2 type substitutions. So let's run through these real quick. Then I want to hit one more concept about ranking nucleophiles. Then we're gonna jump on to elimination, and we'll do elimination today and Friday, and probably start another topic on Monday. All right. So let's do this top example up here. I'm gonna cut it out so we can have more room to work. So let me see if I can grab it. Add a page. All right. Let's see what we can do with that one. And while we're doing it, we're gonna also add some more elements to it other than just drawing the products out. Uh-oh. Come on. All right, here we go. All right. So let's look at the first example. Let me just zoom out a little. Can y'all still see that? So
Yeah.
the first example is here. I'm gonna abbreviate that. This nucleophile here is OAC. So I'm gonna abbreviate it.
My job.
All right. So we're not asking for the mechanism or how it happens, because we already know the mechanism. If it's a SN2 or SN1. Right here, with this being a secondary carbon, what can we say about that?
You would say it's tertiary because it's bonded to the chlorine too.
It's not tertiary. The chlorine doesn't count when you're counting bond order. So the carbon where the chlorine is a separate functional group. So that carbon only has 2 bonds to carbon. So it's considered a secondary. Say again?
So you only count how many carbons is attached to each?
Yes.
Oh, okay.
All right. So we have a secondary carbon. We don't have the solvent, but what can you say about a secondary carbon? What do you know? What about substitution mechanism? Which substitution mechanism it'll go through?
SN.
Can it do both?
Yeah, both.
Yes, it can do both depending on the solvent. If it's in a protic solvent, it's going to be SN1. If it's aprotic, it's going to be SN2. So let's just draw the product, right? So that's the substitution product where the acetate anion is the nucleophile. And this is my substrate. And it could be SN1 or SN2. Without the solvent, we don't know. All right, let's do the next one. Let's do
I know you care about everyone in the village, and so do I. You and Mother and Grandmother and everyone. That's why we have to fight.
all right. Let's do the next one. Let's do B. Come on now. So iodine is my leaving group, and I'm reacting this with Na plus Cn minus. What's the product going to be? All of these are substitutions, by the way.
The CN would be where the I is.
Thank
And
you. Who was
then
that?
I and Miss Baldwin.
Miss Baldwin. All right. Got you, Miss Baldwin. So the cyanide is my nucleophile. So that's just going to replace my leaving group. That's anytime you're doing a substitution, that's the outcome, right? Whatever your nucleophile is going to replace the leaving group, right? And then if I wanted to keep track of everything, it would be plus sodium iodide. Are we okay with that? All right. What about C? Now, before we do C, if that iodide, with it being on a primary carbon, what mechanism is that? By mechanism, you do understand what I'm saying, right? Is it a SN2 mechanism? Is it a SN1 mechanism? Which mechanism is it going to follow?
SN2.
SN2. It's a primary carbon. It cannot do anything other than SN2. It will not undergo SN1 because of the carbocation intermediate. All right, let's do C. Let's do C. What do you know about C right away? Mechanism wise. Can it do SN1, SN2?
Yes, not. Wait.
Was that a yes?
No, it can't be SN2.
Can't be SN2. Why not? Help me out. You're right.
Because a tertiary carbon is the worst kind of
Yes. For SN2, you cannot have a tertiary carbon. It won't happen on a tertiary carbon. I think that was the last thing we talked about in class the other day too, because the tertiary carbon is too sterically hindered. Right, so that can only do SN1 if it's doing substitution. What's the product? Water is my nucleophile. Right, so that's what it's the oxygen that's going to attack. What's the product going to look like? Will this be an OH?
Yeah, OH.
Plus what?
Plus
HI.
HI.
Right, there will be an intermediate. Well, that actually will be, let me show you so you don't get confused. There actually will probably more than likely be two intermediates. Let me add another page right quick. Just in case I run out of space. Right, so you're going to have, obviously you're going to have this carbocation intermediate, right? And then once water attacks, right, once that attacks that carbon, you're also going to have this intermediate. And that oxygen is going to be positive. And then this will be plus I minus, which will just come in and do proton transfer. All right, so that's how you would get to here. So knowing that, if you had to draw an energy diagram for that reaction, how many steps would it be? And what would the rate determining step be? we could start here, right? What's the first step in an SN1?
The nucleophile, I mean, not the nucleophile, the leaving group leaves.
Who is that?
Needed.
Okay, come on with it now. You're telling the truth. Leaving group leaves, right? So your intermediate is here. Sorry about that. Right, so it's that plus I minus. So that's the rate determining step, yes?
Yes, you talking about the
leaving
step when the leaving group
yeah,
leaves?
leaving group leaving.
Yeah.
That's your for SM1, that's your rate determining step. So then that's one step in the reaction. So let me go down here, and that's rate determining, so it's gonna have the highest activation energy. Right, that'll get me to my carbocation intermediate. What's the next step?
The nucleophilic attack.
Of the water. Yep. So that's that. That's gonna get me to that intermediate. So this is let's number them. So this is step 1. And then this will be step 2. And then this will be step 3. Is that right? The proton transfer, which is always going to be a rapid reaction. Are y'all following that? So the reason I'm asking about the energy diagram is because I want you to see that although it's SN1, and we say that SN1 is stepwise, if it's a part of a larger reaction, then there are going to be other steps as well, right? So in this case, you have actually 2 intermediates. And then on the energy diagram, this is time on the x-axis, and then energy on the y-axis. Right, but the activation energy is always going to be highest for that rate determining step. And how do I know what the activation energy is? Not quantitatively, but qualitatively. How do I know what the activation energy is? Because I don't have a number, right? So what am I looking at to say the activation energy of that first step is higher than the rest of them?
Where the reaction starts and then to how high it goes to the peak.
Right. So I'm looking here, right? So these are my reactants. And I'm looking at the distance between here, where the reactants are, and the transition state. I gotta erase this H. Right, so the distance between the reactants and the transition state, that's my activation energy. Or if you learn this in part in G-Chem, right? Delta G, double dagger. If you didn't learn it in G-Chem, then you learn it in Organic 1. Right, so that's my activation. That's how I know which one has the highest activation energy. All right, let's move on to another example, unless there's a question. Somebody tell me what the answer to D would be. Can y'all see that? We're doing D. What would it be? You know it's still gonna be, the product is still gonna be a ring. Let me not draw it on that line because it's gonna get cut off.
Well, the carbon is tertiary, so would it be a SN1 again?
Yeah, it is another SN1. You're right about that. So what's going to replace chlorine? That's what I'm asking. Is it the highlight? What I just highlighted?
Yeah.
So it'll be. I'm gonna abbreviate it as O-ethyl, OET. Come on, Russell, get your mind right. You was late, and now you can't write. Let me just do this. All right, so O-ethyl plus what?
HCl.
Good, good. Plus HCl. That's good. I'm glad you caught that. All right. Can somebody tell me what about E? What's the nucleophile in E? What's the nucleophile?
Be that alcohol. Wait, is that alcohol? The
OCH3.
Yeah, it's a it's an alkoxy. So you close. Right? It's the OCH3, not the sodium. The sodium is what? What do we call that? And what did y'all call that in GChem? Y'all working with salts.
A base?
Mm.
No, it's not a base, it's a counter ion, right? If the OCH3 is negative, which it is, and it's got 3 lone pairs around oxygen and negative charge, the sodium is a counter ion in it, positive, right? So that's the part, the OCH3 is the nucleophile. It's the nucleophilic part of the nucleophile. All right, so what's the product gonna look like? Because if that's the nucleophile, then this is my what? My substrate. Is that right?
Mm-hmm.
And what type of substitution do you think it is going to be? We know this one was an SN1, but SN1 because it's on a tertiary carbon. This one's on a secondary carbon. What does that mean?
It could be SN1 or SN2.
It can be either or. Depending on what?
The solvent.
Solvent. If it's protic, it's probably going to be SN1. If it's aprotic, it'll be SN2. And so what would the product look like? I'll write that one down.
Wait, the sodium and the OCH3 is the nucleophile, both of them?
No, the whole salt is your nucleophile, but it's only the OCH3 that's nucleophilic. The sodium is just there as a counter ion because that oxygen is negative. So you gotta have something to balance it, neutralize it. So that's what the sodium is there for. It's a salt.
Substitute
But
the bromine.
Yes, when the reaction happens, the bromine is going to get swapped out with OCH3. And when that leaving group leaves as Br minus, what do you think that sodium is going now?
To the bromine.
NABR.
It's going right here, right? Because it's positive. That sodium is only there with the OCH3 because it's negative. As soon as that OCH3 reacts with a electrophile, then the sodium is going to find somewhere else to go.
BR and NA aren't combined; they're just flowing.
Yeah, it's the salt. That's a electrostatic attraction. Remember when we in organic 1 we talked about different intermolecular forces, hydrogen bonding, dipole, van der Waals, and then ionic. That's an ionic attraction between those two.
Okay.
All right, let's do is that the last one? We're running through these. Tell me what the product is for F. I'm gonna write it down here again so we can have room to discuss it. Let's think of Cl plus S I'm gonna put this in parentheses. So this is my substrate. Chlorine is a good, very good leaving group. And then this is my nucleophile. What do you think? Sulfur is the nucleophile. It has a pair of electrons that can attack right here at this carbon and kick off chlorine. So what are we going to get?
Is it SN2?
So yes, it's a SN2. That's right. And then is sulfur going to have a charge on it? Right, it's going to be positive. Sulfur and oxygen are in the same group on the periodic table. So when it attacks, now it has 3 bonds to it, so it's gonna have a positive formal charge. All right, and then the chlorine is here. All right. Any questions about these substitutions? I think that's enough information on SN1 and SN2 that I think you should be pretty comfortable with that. On your own, you should be able to finish this problem right here, where it says draw the substitution product that results from 1, 2, 3, 4, 1 bromide and reacts with each nucleophile. So it gives you the nucleophiles. For NaN3, that is the N3 is what you call an azide, and it's a negatively charged nucleophile. All right. Anytime you see sodium, whatever that sodium is with, it's going to be negative. All right. So let's look at this last question. It says rank the species in each group in order of increasing nucleophilicity. If you had a chance to watch that video that I sent out, there was quite a few actually, but the ones dealing with ranking nucleophiles, there are some trends, periodic trends on that video where you can figure out what the nucleophilicity is roughly, qualitatively, based on its position on the periodic table. What is the trend, the periodic trend, if the solvent is protic?
And it decrease from left to right, and
isn't it
to
decreasing?
bottom, I think.
So in a protic solvent, nucleophilicity is decreasing from left to right. I agree. And then is it increasing or decreasing from top to bottom?
I want to say it's
Increasing top to bottom.
Okay.
Yeah, increasing. Yeah.
Other one then. My bad.
So it's decreasing from from left to right, and then from top to bottom, it is increasing. In a protic solvent. Right? What about in an aprotic solvent?
Decreasing left to right, and then decreasing top to bottom.
So decreasing and decreasing. Is that right?
Yep.
Yes.
Good. That makes me feel good that y'all actually watched that and took notes.
I just got them confused, the aprotic and protic.
Who said that? Let me reach through this thing.
No, don't do that. Don't do that.
Who is that?
um,
You can tell me now because I can pull it up and see. Go ahead. Now I'm just joking. I'm not gonna reach through the thing. That's not possible.
it's Ariana.
Okay. So Protic is again a solvent that can donate H plus, like an alcohol, an acid, water, anything that has a proton that it can donate.
Right. Okay.
Right. So think about. I'll put it like this: a proton on a highly electronegative atom, right? Like
Hmm.
OH or HCl or HI or anything that can has a proton that can be donated is protic,
Right.
right? And when you donate protons, what you end up doing to your nucleophile is surrounding it with protons. It's called salvation. I got a link I want to send y'all. I was looking at this morning. It's really good. Let me see if I can share it. Mm, what is the link? I'll email it. I'll send it out in the announcement. let me email it to myself. It's really good. It's dealing with this topic right here, as a matter of fact. Let me just email it to you.
Question. Okay, so when it comes to this nuclear, like putting them in order, how do you do it in regards to these molecule groups?
That's what we get ready to do now.
Oh, okay.
Yeah. All right. So we got the trend established, right? Protic solvents nucleophilicity is decreasing from left to right and increasing from top to bottom. And then in an aprotic solvent, it's decreasing from left to right and it's decreasing from top to bottom. All right. So now in these examples, it's giving you a group of nucleophiles. Let's look at A. You got CH3 minus, so that's a carbon nucleophile. The negative charge is on carbon, OH minus, and NH2 minus. And it doesn't give you a solvent. So we're going to assume that it's in an aprotic solvent. If there's no solvent listed, you assume it's aprotic. So where is carbon relative to oxygen and nitrogen? Is carbon the furthest to the left on the periodic table? Do we need to pull up a periodic table?
Yes, the furthest to the left.
Yeah, so it's carbon, then nitrogen, then oxygen, right? Because group 4 is carbon, group 3 is boron, carbon, nitrogen, oxygen, and then group 7, which is your halogens. All right, so so which one of those is the best nucleophile?
CH3 minus.
The carbon. Good. This is the best nucleophile. And what do you want our ranking to be? One is the best or 3 is the best? Because it's relative, right?
1 is the best.
Okay, so 1 equals best, and then 3 is worst. Keep running out of room, man. I miss having a whiteboard. Like I really do. But I also like not being. Never mind. I'm gonna leave that alone.
Like
One is
not
the best.
looking at
3 is the worst. What'd you say?
nothing.
Yeah, we're gonna leave that one right where it is. Let the dog stay asleep. 1 is the best. 3 is the worst. So if the carbon nucleophile is the best, and then as we move to the right, nucleophilicity decreases. So what's the worst one?
The oxygen.
Oxygen. Good. So this is 1, and then oxygen would be 3. And it's kind of weird, like the rules for nucleophilicity are really weird, right? Because sometimes the nucleophilicity and the basicity parallel each other, sometimes they don't. The oxygen is more electronegative, so it's less apt to give away its electrons. So it's really really nuanced. So we have to use our best judgment and then use the rules that have already been established through research, right? So these are the trends that are known, and so that's what we're rolling with. All right, let's do.
Can you go over again? How did you find out it's a protein or make that guess?
Because there's no solvent listed, right? Let's look at the next one. You'll see what I'm talking about. So you
Okay.
see on B, you see how it says right here, it says NCH3OH or N-methanol.
Okay.
So methanol is a protic solvent, right?
Quick question.
Yeah,
I could be wrong, but from the
that's
video,
okay.
it was like DMF was
Yeah.
is that made it aprotic if that was a solvent?
Say that again. Yeah, DMF is an aprotic solvent.
Okay, just make sure, just
Yeah,
because.
yeah,
Okay.
yeah. So DMF is aprotic, acetone is aprotic, THF is aprotic, ether is aprotic. There's a whole list of solvents in this handout, protic and aprotic.
Okay.
My suggestion is to drill them. Just keep going over them until they stick. But if you ever see an alcohol like methanol, ethanol, or water, any type of acid or alcohol, is protic. All right. So what's the trend here in protic solvents or in protic solvents is decreasing from left to right and increasing from top to bottom. Is that right?
Right.
So for B, both of those first two, oxygen is your nucleophilic atom, right? So you got to choose between OH minus and water. Which one do you think is better between those two? Think back to organic one, right? A negative nucleophile is always better or more nucleophilic than a neutral nucleophile. Are you following that? Do you remember that rule from organic one?
Yes.
Negative nucleophile is always better than a neutral nucleophile. So between the water and the hydroxyl anion or the hydroxide anion, which one of those two you think is best?
The hydroxide.
Yeah, the hydroxide because it's negative. And then between the hydroxide and the sulfur, which one is best? Think about the periodic table. We're in a protic solvent. So decreasing from left to right, increasing from top to bottom. Sulfur is under oxygen. So is sulfur a better nucleophile?
Yes.
Yes. So which one is best?
The sulfur
Sulfur is best,
and then the hydroxide.
and then water is the worst, right? So that's sulfur was in this case sulfur is going to be the best or one, and then water is going to be 3. Is that right? And then the hydroxide is in between them. Because we said 1 is the best, and then 3 in class.
So you got that one is the best because it's a negative, and water is last because it's neutral.
Yeah, but so it's not just that it's negative because the hydroxide is also negative. It's the fact that sulfur is under oxygen in the periodic table. And in a protic solvent, we said up here that the nucleophilicity decreases from left to right and it increases from top to bottom. So as you go down a group in the periodic table, in a protic solvent, the nucleophiles get better. Is that right?
Yes.
Hold up, let me. All right. Did that answer your question? All right, let's do C. Let me erase this up here. All right. C is a tricky one. So you're in methanol again. So you're in a protic solvent. All right. What are we looking at? Which one of those is going to be the best?
The sulfur is gonna be the best.
Sulfur. Exactly. So this is 1. So between the ethoxide anion, which is here, it's an ethyl group. It's connected to a negatively charged oxygen, so we call it an ethoxide. But between that and the acetate anion, which one do you think is best? I'm gonna have to write this out, so I'm gonna make it make some room somewhere. Go down here. I gotta add a page right quick. Hold up. Add a page. All right. Man, people just so disrespectful. Trying to teach the cherries. And they just keep texting, calling. All right. So we had CH3, CH2S. Is that right? And then we had CH3, CH2O minus. And then the acetate was CH3, C double bond O minus, right? When you see that abbreviation written like that, COO, it's really a shorthand way of writing a carbonyl. Or right? So it's like a shorthand way of writing that carbonate anion. All right. So we know this one was the best. We already agreed that that's the best nucleophile because you're in methanol again, so you're in a protic solvent. Sulfur is under oxygen, so it's a better nucleophile in that situation. What about the other two? Which one do you think is the best? And somebody tell me why you think it's the best. Anytime you give an answer, you gotta be ready to defend it.
The COO,
You say that's the
Ethanol.
best.
I believe so.
Why do you say that?
Because if the solvent is protic, and we use the little chart, or the periodic table, basically O. I don't know. It has 2 O's, so I thought maybe.
So let's think about it. Both of these are oxygen, right? How many? If you watch the video, the last video I sent with the examples in it, what does resonance do to a nucleophile? Does it make it better or worse?
Worse.
It makes it worse because the charge is delocalized. So instead of this being a good nucleophile, now the electrons are tied up in resonance, right? So it lessens its nucleophilicity, right? Because now the charge is delocalized over those 2 atoms, and while the electrons are tied up in resonance, they're not readily available to act as a nucleophile, right? And so resonance weakens this as a nucleophile. It's going to make it a not as good of a nucleophile, right? So we're gonna give this 3. We're gonna label this one as 3, and label that one as 1. So 1, the sulfur being the best, and then the acetate anion being the worst because of resonance. Is that clear? Does that make sense?
Yes.
Yes.
All right. All right. Let's do another one. But we got time. We got 12 minutes. All right. Let's do. Somebody help me with D. Now you in acetone. Acetone is a aprotic solvent. So there's a reason why they're saying protic or aprotic. That's to keep you thinking between the trends and not getting locked into a box, right? What do you think? it's the nitrogen, the sulfur, or the oxygen that's going to be the atom that donates electrons as a nucleophile. But you're in acetone, so you're in an aprotic solvent. So which one of those is going to be the best?
It's decreasing.
From left to right is decreasing, and from top to bottom is decreasing.
So the nitrogen will be the best.
Yes, nitrogen is your best, and then what? Oxygen,
Oxygen, then sulfur.
and then sulfur. Good. So this is one. Let's zoom in on it so I can write halfway decent. That's one, and then the sulfur is going to be 3. Because we said 1 was the best and 3 was the worst. So if you were to rank it, like the question asks, in order of increasing, it would be 3, 2, and then 1, right? So sulfur, oxygen, and then nitrogen. Is that cool? We okay so far?
Wait, what? Wait, you said you was to put it increasing, you'll do it backwards?
Yeah, if it asks you to rank in order of increase in nucleophilicity. So if you had to list them in the order of worst to best,
Oh, okay.
you feel me? It would be sulfur, then oxygen, and then nitrogen. Or 3, 2, 1. Because we said we gave sulfur the worst designation, right? So it's 3. All right. What about E? Somebody do E real quick.
Mm.
You're in acetone, you're in aprotic solvent. The trend is
Oh.
decreasing
So
left to right and decreasing.
Oh, wait, do we look at the O?
Yeah.
Okay.
So let
The O is
me make
1.
that point kind of clear too. When you're talking about a nucleophile, what is a nucleophile? A nucleophile is what? An electron pair donor. So the only atoms that that donor looks so sick, like it's on crack. Sorry about that.
It's the sound of frustration that makes it more funny.
Yeah, I get frustrated a lot. It's just life is rough, man. But the only atoms that can be nucleophiles are atoms that have lone pairs of electrons. Right? So when we're talking about go back up to D, it's not the carbon or the hydrogen, it's the nitrogen, because nitrogen has a lone pair. Or sulfur in this case will have 2 lone pairs. Oxygen will have 2 lone pairs. So when you talk about nucleophile, you're only looking at atoms that have electrons to give away.
Okay.
Right? So here, like this, right? Oxygen has 3 lone pairs in this case. Fluorine has 4 lone pairs. Chlorine has 4 lone pairs. Right? So that's what you're thinking about when you're thinking about if something is a nucleophile. It's got to have electrons to donate.
Okay, then it'll be is it hydroxide, fluorine, and then chlorine?
Yes.
Fluorine.
Yes. Because the hydroxide is the furthest to the left, and then you go fluorine and then down, and you're in acetone, so it's decreasing from left to right and from top to bottom. So you're right. Right. So your oxygen is gonna be, we're gonna label that one 1, and then chlorine we'll label 3. Good. That's good. All right. The last one, somebody do that one. It's in methanol, so it's in a protic solvent.
It's first.
Sulfur is first.
Yeah, sulfur is
Yeah,
first.
sulfur is first.
Yeah, even though it's under fluorine, it's still further to the left of it. So you're right. Sulfur is first, and then what?
Fluorine.
Then Cl.
Chlorine and fluorine.
Yep.
Yeah,
Yes.
chlorine different.
Yes. Yes. Good. So sulfur is going to be 1, and then this is going to be fluorine is going to be 3. All right, we're okay with that. Hopefully the video kind of helped you or prep you for that. How to determine what I know it was a lot, but it's a more nuanced uh, topic than it looks like on the surface. All right. How much time we got left? 6 minutes. Let me go back up to let's see. Let me skip that. Back up to the top. All right. So we talked about SN2 and SN1. And so now I want to start talking about elimination in the last few minutes, and then we're going to stop. So what do you remember about elimination from part 1? What's the outcome of any elimination?
Uh,
You always,
I thought it was breaking a double bond.
well,
I don't
no, that's
see now.
addition. That's addition. When you eliminate, elimination always makes a double bond or a pi bond.
Oh,
Right?
okay.
That's how you know you've done an elimination, is when you form a pi bond. Right. So let's look at that for the E2. Right. It talks about, it gives you over here the different characteristics. So a tertiary, I'm gonna do the second one, by the way, because the top one is kind of, it won't give us, it won't teach us a lot, but the second example will teach us a lot. So the top one, the characteristics, you favor tertiary carbons, right? Because when you eliminate from a tertiary carbon, you generate a tri-substituted alkene, which is more stable. We can talk about that, so don't panic. You need a strong base, and it follows Zaitse's rule. And let me add one more thing to that. Zaitse's rule just says that the more substituted alkene is going to be your major product. We'll talk about that. And then let me add one more thing that you need. I think this was a quiz question too. One of them anyway. That the geometry must be what we call anti-periplanar. Let me write that whole word out. Anti-periplanar. What that means is that the proton that you're removing and the leaving group have to be on opposite sides of each other. So I want to look at this first substrate right here. I'm just going to point out what's going to happen, and then we're gonna run out of time. But I want to show you where the action is happening. And then I think I already sent the elimination videos to you, so you might want to watch those again before Friday. So when you come back, we can just jump in, right? So the thing about elimination, first thing you need to do is find a leaving group. Always locate your leaving group first. Once you find a leaving group, then you'll know which protons are coming off, right, for your elimination to happen. So when you find a leaving group, the carbons that are adjacent, get a different color here and here, those carbons have hydrogens on them that are going to get removed by the base. That's why you need a base. So this is my base. Right, there's a whole bunch of different bases you can use. I think, no, never mind. I'm mixing this class up with my other class. There's a whole bunch of different bases you can use. So these protons that are here, And then that one there, those are called alpha protons. Those are the hydrogens that get pulled off during elimination. And the E2 is just like SN2 in that it's concerted. So when the elimination happens, everything all happens at the same time, right? So when I eliminate, let me just illustrate that, and then we're going to stop. So the base, the OH part of the base anyway, that's coming in here. Boom, it's going to take off that hydrogen. Either one of them can come off though, but I'm doing that one because I don't want to have it all jumbled up on the other side. When that happens, the next thing that happens is this pair of electrons come in here, right? And then I lose my leaving group. So if you notice, the hydrogen right here, it's up here, and the leaving group is on the opposite face. So that's what that anti-periplanar is. If I draw like a Newman projection for that, hopefully y'all remember that from organic 1. Let me pick a different color. So the Newman projection will look like this, where the hydrogen is here, and then the iodine is here. And I'm gonna draw it. Oh no, sorry about that. I'll draw it staggered. Right? So the iodine is always gonna be opposite from wherever that alpha hydrogen is. That's what the anti-periplanar geometry looks like. Come on, man. Right? So anytime the elimination happens, the base is going to rip off a proton on one side of the plane, and those electrons that from that CH bond are going to force that leaving group out that's on the opposite side of the plane. So that's what the whole anti-periplanar thing means. And then so based on that, and this is the last thing I'm gonna say, and then we're done. So based on that, you should get a pi bond right here, right? When you push that pair of electrons from the CH bond there and lose the leaving group, you should get a pi bond there, right? So that's that's the basic mechanism for elimination. The base comes in for E2 elimination. Base comes in, pulls off that proton. You use those electrons to make a pi bond and force the leaving group out at the same time. It's a little bit more nuanced than that, but for the scope of this class, I think that's enough information. All right, and so when we come back on Friday, we're going to talk about the E2 and the products. We'll talk about the E1, which is a little bit different, a little bit easier to understand than E2. And then we'll be done with this section. And possibly on Monday, we'll start another section, possibly. I have to see what's coming up next. And if it's something big, I don't want to try to cram it in because I'd rather y'all learn it than us just to get through it. So, all right, any questions? It's bad. Start late and then end late.